Right now, the universe is expanding so rapidly that every single second, the distance between faraway galaxies stretches by thousands upon thousands of miles. But here's the part that completely shatters our understanding. It's not expanding into anything at all. There's no cosmic storage facility waiting out there, no outer edge, no larger container standing by to be filled. We're about to embark on a journey through what might be the most mind-shattering concept in all of science. We'll explore how space itself generates its own existence from absolute nothingness. We'll witness the invisible force that's literally tearing the fabric of reality apart at the seams. And we'll discover why asking what the universe is expanding into is fundamentally similar to asking what lies north of the North Pole. Steel yourselves. We're diving in. Picture a balloon expanding inside your living room. As you force air into it, the rubber material stretches outward, pressing against the surrounding air. The balloon grows larger, specifically because there's available space for it to occupy. Your living room provides that necessary space. This makes complete and total sense to our minds. This is precisely how expansion functions in our everyday lived experience. But the universe completely mocks this intuitive logic. When cosmologists inform you that the universe is expanding, your mind automatically conjures that balloon image. You visualize space stretching outward into something else, some kind of cosmic room, some enormous emptiness sitting there waiting to be occupied. You naturally think there must exist a boundary line where our universe terminates and something entirely different begins. This mode of thinking feels completely natural. It feels undeniable. Here's exactly where physics demolishes your comfortable assumptions. The universe bears absolutely no resemblance to that balloon whatsoever. When space expands, it doesn't push into anything external to itself. There exists no cosmic living room. There exists no container. There exists no outside. The universe creates the fundamental concept of space itself as it continues growing. Consider it this way. Imagine attempting to draw a circle that's larger than your sheet of paper. But rather than acquiring a larger sheet of paper, the paper itself expands to accommodate your circle. This sounds completely impossible because in our immediate world, everything expands into something else that already exists. Plants grow into surrounding air. Cities spread into the countryside. Ice spreads across water surfaces. Always, without exception, there's a destination for the expansion to occupy. Always, there's a boundary line between what's expanding and what it's expanding into. But what if you yourself are simultaneously the paper and the drawing? What if there's no separation between the canvas and the creation? Scientists uncovered this absolutely mind-bending truth by carefully observing distant galaxies. Edwin Hubble made the observation that galaxies positioned farther away from our location are racing away at higher velocities than nearby ones. Initially, this appears to suggest we're positioned at the center of some massive cosmic explosion, as though we're sitting in the middle while everything else flies outward into empty space surrounding us. The actual reality is monumentally stranger than that simple picture. Space itself is stretching. The galaxies aren't traveling through space at all. The space that exists between them is actively growing. Imagine dots on a deflating balloon, but reverse the entire process in your mind. As the balloon inflates, the dots get farther and farther apart without actually moving on the surface itself. The surface itself expands and carries them along. Each individual dot observes every other dot moving away from its position. No single dot is special or privileged. No single dot sits at the center of the expansion. Now replace that two-dimensional balloon surface with the 3 dimensions of space you actually live inside. The universe isn't expanding into anything because there exists no anything for it to expand into. It's generating the very stage upon which expansion can possibly happen. This demolishes our intuition so completely and thoroughly that even the most brilliant scientists struggled with it for multiple decades. Albert Einstein himself initially rejected this entire idea outright. Yet this seemingly impossible expansion is occurring right now, at this very moment, faster than you could possibly imagine. But how can we be absolutely certain this bizarre process is genuinely real? The answer lies in watching light itself get tortured by the expansion of space. When a distant galaxy launches a beam of light in Earth's direction, that light begins its incredibly long journey with a specific wavelength. Blue light, red light, infrared radiation. Each wavelength carries a unique signature resembling a cosmic fingerprint. But as the light travels through expanding space, something truly extraordinary takes place. The space the light moves through actively grows larger during its journey across the cosmos. Imagine you're walking across a moving walkway that's slowly stretching as you walk forward. Your individual steps remain exactly the same size, but the ground beneath your feet keeps growing longer and longer. By the time you reach the opposite end, you've traveled significantly farther than your steps alone should have taken you. Light experiences something remarkably similar, but instead of traveling farther, its wavelength gets progressively stretched. Blue light from a distant galaxy arrives at our telescopes, transformed into red light. Not because the galaxy moved away from us like a speeding ambulance changing the pitch of its siren. The light becomes redder specifically because space itself expanded during the light's billion-year journey across the cosmos. Each individual wave of light gets pulled longer as the cosmic fabric grows beneath it as it travels. This process, called cosmological redshift, provides definitive proof that space grows independent of the objects within it. Here's the number that will completely rewire your brain's understanding. Light from the most distant observable galaxies has been stretched to nearly 40 times its original wavelength. The space that light traveled through expanded so dramatically that what started as intense ultraviolet radiation now reaches our instruments as faint infrared heat. 40 times longer wavelengths mean the universe expanded by a factor of 40 during that particular light's journey. Think carefully about this profound implication. The galaxy that transmitted this ancient light appears tiny and extremely faint in our most powerful telescopes. But when that light first departed the galaxy, the universe was 40 times smaller than it is at this very moment. That galaxy was substantially closer to where our Milky Way would eventually form billions of years later. Space didn't just grow a modest amount. It underwent massive, absolutely relentless expansion. But here's what makes this even more profoundly mind-bending. This stretching isn't happening somewhere else far away. It's happening everywhere simultaneously. Right now, at this exact moment, the space in the room where you're sitting is attempting to expand. The space between your eyes and the screen you're looking at wants to grow larger. The only reason you don't personally notice this expansion is that electromagnetic forces between atoms are vastly stronger than the expansion rate. Only across enormous cosmic distances does this expansion become truly noticeable. The space between galaxies has no atomic forces to hold it together tightly, so it expands freely, carrying those galaxies along like raisins distributed throughout rising bread dough. The raisins don't move through the dough itself. The dough expands and carries them apart. This is precisely why the question, "What is the universe expanding into?" breaks down so completely and thoroughly. You're asking what the dough is expanding into, but you yourself are part of the dough. Everything you can possibly observe is part of the dough. There is no outside perspective from which to view the dough expanding into something else. However, if space is stretching everywhere simultaneously, how far can we actually see into the cosmos? We live inside the ultimate cosmic prison, and the walls are constructed from time itself. Every night you step outside and look upward at the stars scattered across the darkness. You feel like you're seeing the universe, the whole thing, all of reality stretched out above you in that dark sky. But here's the truth that will fundamentally reshape how you think about existence itself. You're seeing less than 4% of what's actually out there in the cosmos. You're trapped inside an invisible sphere. This sphere has a radius of approximately 46 billion light-years. Beyond this boundary lies more universe, billions more galaxies, trillions more stars, perhaps even other versions of you reading these exact words, right now in distant regions of space, but you will never, ever see any of it. Not with any telescope humanity could possibly build. Not with any technology that could ever exist, even in principle. The trap isn't constructed from walls or physical barriers of any kind. It's constructed from the finite speed of light combined with the finite age of the universe. Light takes time to travel across distances. When you look at the sun in the sky, you observe it as it existed 8 minutes ago. When you look at the nearest star system, Alpha Centauri, you observe it as it existed 4 years ago. Look at the Andromeda Galaxy, and you're seeing 2.5 million years into the past. The farther you look outward into space, the deeper you peer into history itself. Here's exactly where the trap closes completely around you. The universe is approximately 13.8 billion years old. This means the oldest light that could possibly reach your location has been traveling for 13.8 billion years. Any galaxy farther than 13.8 billion light-years away might as well not exist from your observational perspective. Its light simply hasn't had enough time to reach you yet. But wait, the trap gets even more confining and restrictive. Remember that space has been expanding this entire time throughout cosmic history. That distant galaxy was substantially closer to our location when it emitted the light we observe today. By the time its ancient light reaches our telescopes, expansion has carried that galaxy far beyond the 13.8 billion light-year mark today. That same galaxy sits approximately 46 billion light-years away from our position. This creates your cosmic prison cell. Everything beyond 46 billion light-years from Earth exists in what scientists call the unobservable universe. You cannot see it. You cannot detect it through any means. You cannot prove it exists through observation. Yet logic and mathematics tell us it absolutely must be there. Think of yourself standing in a dense fog that limits your vision to 100 yards in any direction. You can see a circle of ground around you, but you know with certainty the world continues beyond that fog. The observable universe is your fog-limited circle, while the actual universe stretches infinitely in all directions beyond what you can possibly see. Here's the number that should simultaneously terrify and amaze you. If the universe is truly infinite in extent, then your observable bubble contains exactly 0% of what actually exists. 0%. An infinitesimally small fraction of infinite reality. But what lies beyond our cosmic prison walls? What exists in those unreachable regions? The most ancient light in the universe is screaming toward you right now at 600 million miles per hour. And it carries a message from the moment reality first began. This light has been traveling longer than Earth has existed, longer than our solar system formed, longer than our galaxy took its current spiral shape. This light began its incredibly long journey when the universe was only 380,000 years old. Back when the cosmos was a seething ocean of plasma, so hot that atoms couldn't even form stable structures. We call this ancient radiation the cosmic microwave background, and it's everywhere around us. Turn on an old analog television set between channels, and approximately 1% of that static comes from this primordial light. You're literally seeing the afterglow of creation itself flickering across your screen. This radiation fills every cubic inch of space throughout the observable universe. It comes from every direction at once. It's the oldest thing human eyes can detect through any means. But here's what makes this discovery so profoundly important. This light represents the absolute edge of everything we can possibly observe. Before that moment, 380,000 years after the Big Bang, the universe was completely opaque to light. Imagine trying to see through the surface of the sun. The early universe was like that everywhere simultaneously. A thick fog of plasma that blocked all light from traveling. No photon could travel more than a few inches before colliding with charged particles and getting absorbed. Then something miraculous happened that changed everything. The expanding universe cooled enough for protons and electrons to combine into the first hydrogen atom. Suddenly, the cosmic fog lifted. The universe became transparent. Light could finally travel freely across space for the first time. The first photons that escaped this cosmic clearing are the ones reaching your eyes today as the cosmic microwave background. This moment, called recombination, created the ultimate horizon for observation. You cannot see past it, ever, under any circumstances. Any events that happened in those first 380,000 years remain forever hidden from view. It's like trying to see through a brick wall that surrounds the entire early universe. The cosmic microwave background is that wall, and it represents the absolute limit of observation. Here's the mind-bending part that really breaks intuition. This horizon moves forward every second that passes. Light that has been traveling for 13.8 billion years, plus 1 second reaches our instruments. The observable universe grows by 1 light second every second. That's about 186,000 miles of new space coming into view. Every day, we can see about 16 billion miles farther into the cosmos. But expansion complicates this growth in fascinating ways. While our observable horizon expands, the actual distance to the source of that ancient light keeps increasing due to cosmic expansion. The galaxy that emitted a photon 13 billion years ago now sits about 30 billion light-years away from our position. We see where it was, not where it is now. This creates a strange situation. We're constantly seeing new regions of space, but the sources of that light are constantly moving farther away from us. It's like watching a movie of someone walking away from you while the screen gets bigger. You see more area, but the person gets smaller and more distant. The cosmic microwave background shows us the universe when it was smoother than a perfectly polished mirror, with only tiny temperature variations of a few millionths of a degree. Those microscopic temperature differences would eventually become everything: galaxies, stars, planets, and life itself. But what happens when we push beyond even this ancient horizon? Past the edge of everything you can see lies more of exactly what you can see. This sounds boring and anticlimactic, but it's actually the most unsettling possibility in all of cosmology. If you could somehow teleport 47 billion light years away beyond your observable boundary, you'd find yourself in a region that looks remarkably similar to here. More galaxies scattered through space, more stars burning nuclear fuel, more planets orbiting those stars, possibly more life evolving on some of those planets. The universe appears to be homogeneous on the largest scales we can measure. Homogeneous means uniform, the same everywhere you look, like perfectly mixed cake batter where every spoonful contains the same ingredients in the same proportions. Our observations of the cosmic microwave background strongly suggest that the universe has this property. The tiny temperature variations we detect are smooth and consistent across the entire sky in all directions. This smoothness tells us something profound about what lies beyond our sight. If the observable universe contains roughly 2 trillion galaxies, then a region of identical size just beyond our horizon should contain roughly 2 trillion galaxies as well. And another region beyond that should contain another 2 trillion. The pattern continues forever, or at least much farther than we can comprehend. But here's where this gets psychologically disturbing. If space is truly infinite and homogeneous, then every possible arrangement of matter within any given volume must repeat somewhere in that infinity. This isn't mystical thinking or wishful speculation. It's a mathematical necessity that follows from basic probability. With infinite space and finite ways to arrange a finite number of particles, repetition becomes absolutely inevitable. Imagine you have a deck of cards and you shuffle it infinitely many times. Eventually, you must get the same arrangement twice. The universe works similarly, but with atoms instead of playing cards. This means there are other versions of you reading these words right now, not metaphorically or symbolically, literally. In regions of space so distant that their light will never reach us, quantum mechanics has arranged matter in every possible way, including ways identical to your current configuration. There are versions of you where you decided to stop reading this sentence, versions where you were never born, versions where the entire history of Earth played out differently. The mathematics suggests these copies exist at distances of roughly 10 to the power of 10 to the power of 115 meters away. That's a number so large that if you wrote it out, the line of digits would stretch across more space than exists in our observable universe. Yet, if space is infinite, these distances are still finite. Somewhere out there, another you is having this same realization about yet another you, even farther away. An infinite chain of identical copies stretching across infinite space. But wait, this assumes the universe beyond our horizon looks like the universe within it. What if it doesn't? Recent observations hint that our local region might be unusual. We seem to exist in a cosmic void, a region with lower than average galaxy density. If this is true, then traveling beyond our observable horizon might reveal denser regions of space packed with more galaxies, more black holes, more activity, or it might reveal regions that are nearly empty. Some theoretical models suggest that cosmic inflation, the rapid expansion in the universe's first fraction of a second, could have created regions with vastly different properties, different physical constants, different particle types, different laws of physics entirely. These pocket universes might exist just beyond what we can observe, operating under rules that would make our physics textbooks worthless. However, there's an even more fundamental question lurking beneath all of this speculation. What if the universe isn't infinite at all? An infinite universe that expands presents one of the most beautiful paradoxes in all of physics. How do you make infinity bigger? Mathematics tells us this should be impossible. Infinity plus anything still equals infinity. Infinity times 2 still equals infinity. You cannot add to something that already contains everything. Yet, our observations clearly show that space is expanding everywhere simultaneously. Even if the universe extends infinitely in all directions, the distance between any 2 points is increasing. So, how does this work? The solution comes from understanding what expansion really means in this context. When we say the universe expands, we don't mean it grows larger in the sense of becoming more infinite. We mean the scale of space itself increases. Think of it like this. Imagine an infinite piece of graph paper where each square is 1 inch wide. Now imagine stretching that paper so each square becomes 2 inches wide. The paper is still infinite. It still has infinitely many squares, but the distance between any 2 marked points has doubled. This is exactly what happens during cosmic expansion. The universe doesn't become more infinite. The scale factor of space increases, making all distances grow proportionally. A galaxy that's 100 million light-years away today was 50 million light-years away when the universe was half its current size. But this creates a disturbing implication. If the universe is infinite now, it was also infinite at the moment of the Big Bang. This means the Big Bang wasn't an explosion of matter and energy from a single point into empty space. It was the simultaneous expansion of infinite space, filled with infinite energy at every location. Wrap your mind around this. The Big Bang happened everywhere at once, across infinite space. There was no center, no edge, no outside. Just infinite space suddenly beginning to expand and cool simultaneously at every location. Every point in the universe can claim to be the center of expansion because expansion looks exactly the same from every location. This infinite perspective solves several cosmic mysteries while creating new ones. It explains why the universe looks the same in all directions from our vantage point. In an infinite homogeneous space, every location is equivalent. It also explains why we don't see evidence of an edge or a center. There is no edge or center to see. But it raises a haunting question. If the universe contains infinite matter and energy, how do we avoid infinite density? The answer lies in recognizing that density is matter divided by volume. Even if both matter and volume are infinite, their ratio can still be finite. The universe can contain infinite stuff spread across infinite space while maintaining a specific average density of about 5 hydrogen atoms per cubic meter. Here's where the paradox becomes deeply personal. In an infinite universe, every possible event that can happen will happen infinitely many times. Not just the repetitions of you we discussed earlier. Every possible version of every possible story plays out somewhere in the vast expanse. Every tragedy, every triumph, every moment of beauty, every act of cruelty, all occurring infinitely many times across infinite space. If this troubles you, consider the alternative. A finite universe raises equally disturbing questions. What lies beyond its boundary? How can space itself have an edge? What happens if you try to travel past that edge? These questions led many scientists to prefer infinite models despite their conceptual difficulties. Recent measurements of the cosmic microwave background suggest our universe is either infinite or so large that any curvature is undetectable by our instruments. The simplest interpretation is that space extends infinitely in all directions. This means the expansion you observe isn't creating new space in the sense of adding rooms to a house. It's stretching the infinite fabric that already exists everywhere. But if space isn't being created, what exactly drives this relentless stretching? The universe manufactures new space from pure nothingness at a rate that would make every factory on Earth weep with envy. Every second, the volume of observable space increases by roughly 10 to the 78th cubic meters. That's a number so massive that if you tried to count that high, one number per second, you'd need more time than the universe has existed, multiplied by itself billions of times. All this new space emerges from the quantum vacuum. Quantum vacuum isn't the empty void you might imagine when you think about empty space. It's a seething foam of virtual particles popping into existence and annihilating each other in time frames shorter than the smallest measurable instant. This process, called quantum fluctuation, fills every point in space with energy. Even in the most perfect vacuum achievable, this quantum activity continues relentlessly. Here's the mind-bending part. This vacuum energy has gravitational effects, but unlike matter, which pulls things together through attractive gravity, vacuum energy creates repulsive gravity. It pushes space apart. The more space you have, the more vacuum energy you get. The more vacuum energy you get, the more space expands. The more space expands, the more room there is for new vacuum energy. This creates a runaway process called inflation. During the universe's first tiny fraction of a second, this process ran completely wild. Space expanded faster than light could travel. Not because anything moved faster than light, nothing can do that, but because space itself grew faster than light could cross it. Imagine trying to walk across a treadmill that accelerates faster than you can run. In less than a trillionth of a trillionth of a trillionth of a second, a region smaller than a proton expanded to roughly the size of a basketball. This sounds like science fiction, but quantum mechanics absolutely demands it. The uncertainty principle tells us that energy can be borrowed from the vacuum as long as it's paid back quickly enough. During inflation, the universe borrowed massive amounts of energy to create new space, then used the expansion itself to pay back the debt. It's like taking out a loan to buy a money printing machine, then using the printed money to pay off the loan. The process worked so well that it overshot dramatically. Inflation should have stopped after creating enough space to solve certain cosmological problems. Instead, it kept going, creating far more space than necessary. Our entire observable universe represents just one tiny patch of the vastly larger inflated region. Think of blowing up a balloon to the size of Earth, then examining just one patch, the size of a pinhead. That pinhead is our observable universe compared to the region inflation created. But here's what makes this truly bizarre. The process continues today in a different form. Current expansion isn't inflation, but it operates on similar principles. Dark energy, which makes up roughly 68% of everything, behaves exactly like vacuum energy. It fills space uniformly and creates repulsive gravity that accelerates expansion. As the universe grows, more dark energy appears to fill the new space. This violates every intuition you have about conservation of energy. Energy cannot be created or destroyed, that's a fundamental law. Yet expansion seems to create new dark energy continuously. The resolution lies in understanding that gravitational potential energy is negative. As space expands, matter becomes more spread out, reducing gravitational binding energy. This negative energy balances the positive energy of newly created dark energy. The universe maintains perfect energy balance while creating infinite new space. This process will continue forever, or at least for longer than human minds can comprehend. Each moment brings new space, new dark energy, and accelerated expansion. The universe grows not because it needs room to expand into, but because expansion creates its own room. Yet all this cosmic creativity pales compared to what happened in that first fraction of a second. What evidence proves this impossible-sounding story actually happened? Hidden in the static of old television sets lies proof of the most violent event in cosmic history. In 1964, two radio astronomers at Bell Labs were trying to eliminate annoying background noise from their antenna. No matter what they did, a persistent hiss remained in their data. They cleaned bird droppings off the equipment. They recalibrated their instruments multiple times. They pointed the antenna in different directions across the sky. The noise never went away. That noise was the echo of creation itself. What Arno Penzias and Robert Wilson had accidentally discovered was the cosmic microwave background, the afterglow of the Big Bang, stretched and cooled by 13.8 billion years of expansion. This discovery earned them the Nobel Prize and provided the most direct evidence we have for the expanding universe model. Here's why this radiation is so profoundly important. It carries the signature of cosmic expansion literally imprinted in its wavelength. When this light first escaped the early universe, it was brilliant, visible light with a temperature of about 3,000 degrees. But as space expanded, the wavelength stretched along with it. What started as intense visible photons became infrared radiation, then microwave radiation, then radio waves. Today, this ancient light reaches us at a temperature of just 2.7 degrees above absolute zero. The cosmic microwave background is perfectly uniform to within a few parts in 100,000. This uniformity proves the early universe was incredibly smooth, just as inflation theory predicts. Without inflation's rapid expansion to smooth out irregularities, we should see dramatic temperature variations across the sky. Instead, we see almost perfect uniformity. But those tiny temperature variations that do exist tell an even more remarkable story. They represent the quantum fluctuations that inflation stretched from subatomic scales to cosmic scales. These microscopic ripples in the early universe eventually became the seeds that grew into galaxies, stars, and planets. You exist because of quantum uncertainty amplified by cosmic expansion. Advanced satellites like the Cosmic Background Explorer and Planck have mapped these temperature variations with exquisite precision. The patterns they reveal match inflation theory predictions so precisely that cosmologists can measure fundamental properties of the universe from this ancient light. We can determine that space is geometrically flat to within measurement error. We can calculate that ordinary matter makes up only about 5% of the total universe. We can measure the expansion rate and age of the cosmos to remarkable accuracy, all from studying static. But the cosmic microwave background reveals something even more profound about expansion. The light shows us that the observable universe today was once compressed into a region roughly the size of a beach ball. Everything you can see in the night sky, every galaxy visible to our most powerful telescopes, once occupied a volume smaller than what you could hold in your arms. This compression wasn't like stuffing matter into a small box. Space itself was compressed. The beach ball didn't contain the early universe. The beach ball was the early universe. There was no outside, no surrounding space, just that compressed region of spacetime beginning its expansion into the cosmos we inhabit today. This realization leads to a disturbing question. If all the space we can observe was once compressed into such a tiny volume, what was providing the energy to drive such dramatic expansion? The answer involves a force that makes up more than 2/3 of everything yet remains completely invisible. How do you detect something that hides in plain sight? In 1998, two teams of scientists set out to measure how much the universe's expansion was slowing down, and instead discovered that expansion is speeding up. This discovery won the Nobel Prize and completely shattered our understanding of cosmic evolution. For decades, astronomers assumed that gravity would eventually win its battle against expansion. All that matter in the universe should act like a cosmic brake, gradually slowing the expansion until everything either stops growing apart or begins collapsing back together. The team studying distant supernovae expected to measure this deceleration. Supernovae of a specific type called type Ia explode with nearly identical brightness. This makes them perfect cosmic lighthouses. By comparing how bright they appear versus how bright they should be, astronomers can calculate precise distances to their host galaxies. When they plotted these distances against redshift measurements, they found something impossible. Distant supernovae were fainter than expected. This meant they were farther away than the standard expansion model predicted. Somehow, space had grown more than it should have during the light's journey to Earth. The only explanation was that expansion itself was accelerating. Something was pushing space apart with increasing strength. Scientists call this mysterious force dark energy, and it dominates everything. Dark energy makes up roughly 68% of the total mass energy content of the universe. It outweighs all ordinary matter by more than 13-to-1. It outweighs even dark matter, the invisible scaffolding that holds galaxies together. Yet we have no idea what it is. Here's what makes dark energy so profoundly weird. It doesn't clump or dilute. Normal matter becomes less dense as space expands. Spread a fixed amount of matter across twice as much space, and you get half the density. But dark energy maintains constant density even as space grows. As the universe expands, new dark energy appears to fill the additional volume. This means dark energy's total influence grows over time. In the early universe, when everything was compressed together, matter and radiation dominated cosmic evolution. Dark energy existed, but its effects were negligible compared to the gravitational pull of all that concentrated matter. As expansion spread matter thinner, dark energy's repulsive influence became more apparent. About 5 billion years ago, dark energy became the dominant force in cosmic evolution. This coincides roughly with when our solar system formed. Before that moment, expansion was slowing due to gravitational attraction. After that moment, expansion began accelerating due to dark energy's repulsive push. We live in the age of acceleration. Every day, dark energy becomes more influential. Every day, expansion accelerates a bit more. This acceleration is subtle over human timescales, but dramatic over cosmic time. In the far future, dark energy will dominate so completely that distant galaxies will accelerate away from us faster than light can travel between them. They will disappear from our observable universe forever. But what exactly is this invisible force that controls the fate of everything? The leading candidate is vacuum energy, the quantum fluctuations that fill every point in space. Quantum field theory predicts that empty space should contain enormous amounts of energy. When scientists calculate how much energy the vacuum should have, they get an answer that's 10 to the power of 120 times larger than what we observe. This represents the worst prediction in the history of physics. Either our understanding of quantum mechanics is fundamentally flawed, or some unknown mechanism cancels out most of the vacuum energy, leaving just enough to drive cosmic acceleration. Alternative theories suggest dark energy might be a new field pervading space, similar to the electromagnetic field but with different properties. Others propose modifications to gravity itself at cosmic scales. The truth is, we are as ignorant about dark energy as ancient humans were about the nature of lightning. Yet this mysterious force shapes everything about our cosmic future, driving an acceleration that began in earnest during an even more dramatic period of expansion. What happens when expansion itself expands faster than the speed of light? During the first trillionth of a trillionth of a trillionth of a second after the Big Bang, the universe expanded more rapidly than it has in all the 13.8 billion years since. This period, called cosmic inflation, stretched space so violently that regions of the universe lost contact with each other forever. Points that were once close enough for light signals to travel between them were suddenly separated by distances that light could never cross. The universe broke its own speed limit. Nothing can move through space faster than light. But space itself has no such restriction. During inflation, the distance between any 2 points doubled every tiny fraction of time. This doubling happened so rapidly that light couldn't keep up with the growing separation. Imagine 2 ants on a balloon that inflates so fast the ants can never walk to each other, no matter how quickly they move. Here's the number that will break your brain. Inflation increased the size of the universe by a factor of at least 10 to the power of 26. That's like a grain of sand suddenly becoming larger than the observable universe today. This expansion happened in about 10 to the power of -35 seconds. To put this timescale in perspective, light travels about 1 foot in a nanosecond. During inflation, the universe expanded by more than 20 orders of magnitude in a time so short that light could cross less than the width of a proton. The energy driving this expansion came from the inflaton field, a hypothetical quantum field that filled all of space. Unlike other quantum fields, which have minimum energy states of 0, the inflaton field got stuck in a high-energy state called a false vacuum. This created a temporary form of dark energy, far more powerful than anything we observe today. While stuck in this false vacuum, the inflaton field drove exponential expansion. Exponential growth starts slowly but accelerates dramatically. If you fold a piece of paper in half 42 times, the thickness becomes equal to the distance from Earth to the Moon. The universe experienced something similar but far more extreme. During inflation, every tiny instant, space doubled, then doubled again, then again. This process solved several major problems in cosmology while creating new ones. It explains why the cosmic microwave background looks so uniform across the sky. Without inflation's rapid expansion to smooth out irregularities, different regions of the observable universe should show dramatically different temperatures. Instead, we see remarkable uniformity. Inflation also explains why space appears geometrically flat. Even if the universe started with significant curvature, inflation stretched that curvature so much that any remaining bend became undetectable. It's like inflating a basketball until its surface looks perfectly flat from your tiny perspective. But inflation's most profound consequence involves quantum mechanics. During inflation, quantum fluctuations in the inflaton field were stretched from subatomic scales to cosmic scales. These microscopic variations in energy density became the seeds that eventually grew into galaxies, stars, and planets. Every structure in the universe traces back to quantum uncertainty amplified by inflation. This means the galaxy you live in, the star that warms your planet, and the atoms in your body all exist because of random quantum events that happened during the universe's first moment. You are the descendant of quantum foam. But inflation raises a disturbing possibility. If it happened once, it might happen again. The same quantum fields that drove primordial inflation might still exist, waiting for the right conditions to trigger another episode of exponential expansion. This could happen here, now, without warning. A new bubble of inflation could nucleate anywhere in space, expanding outward at the speed of light and destroying everything in its path. Inside the bubble, new physics would apply. Our atoms would disintegrate. Our laws of nature would cease to function. We would never see it coming. Yet this terrifying possibility pales compared to inflation's most mind-bending implication. What if our universe is just one bubble in an infinite sea of expanding realities? While you read these words, trillions of other universes might be inflating into existence, each with different laws of physics, different constants of nature, and different possibilities for life. This isn't science fiction. It's the logical consequence of inflation theory. If inflation happened once, quantum mechanics suggests it should happen continuously throughout a larger space called the multiverse. Random quantum fluctuations can trigger new episodes of inflation anywhere, anytime. Each episode creates a bubble universe that expands and cools, potentially developing its own galaxies, stars, and planets. Our universe would be just one bubble in an infinite foam of realities. Here's what makes this possibility so disturbing. Each bubble universe might have different physical laws. The strength of gravity could be different. The mass of electrons could vary. The number of dimensions of space might not equal 3. Most of these universes would be uninhabitable wastelands. In some bubbles, gravity might be so strong that stars collapse immediately into black holes. In others, gravity might be so weak that matter never clumps together to form structures. Some universes might have no electromagnetic force, making chemistry impossible. Others might exist in a state of eternal inflation, never cooling enough for atoms to form. The vast majority of bubble universes would be sterile, but in an infinite multiverse, even the most unlikely possibilities must occur somewhere, no matter how improbable our specific combination of physical constants might be. Infinite bubbles means infinite opportunities for those constants to align perfectly for life. We exist in a habitable bubble not because we're special, but because we can only exist in habitable bubbles. This reasoning, called the anthropic principle, explains why our universe seems fine-tuned for life. We don't live in a universe designed for us. We live in the rare type of universe where observers like us can evolve to ask such questions. But the multiverse concept raises profound philosophical problems. If infinite universes exist, then every possible event happens somewhere. Every decision you didn't make gets made by another version of you in another bubble. Every tragedy you avoided befalls another version of you somewhere else. Every dream you never achieved comes true for another, you in a different reality. The multiverse contains infinite copies of everyone, everywhere, experiencing everything. This infinite replication makes the concept of uniqueness meaningless. You are not unique if infinite versions of you exist. Your choices don't matter if every possible choice gets made by some version of you. Your universe isn't special if infinite similar universe exists alongside it. Yet the multiverse remains unobservable. By definition, other bubble universes lie beyond our cosmic horizon. Their light can never reach us. Their gravitational effects cannot influence us. We can never prove they exist or determine their properties. The multiverse concept makes predictions that cannot be tested. This troubles many scientists who argue that untestable theories don't qualify as science. But the mathematics of inflation strongly suggests eternal inflation and bubble nucleation. The same quantum field equations that explain our universe's early expansion predict ongoing expansion and bubble formation throughout the larger multiverse. If we accept inflation, we must accept its consequences. Recent observations have begun testing inflation's predictions more precisely. The cosmic microwave background contains subtle patterns that match inflation theory remarkably well. These observations strengthen confidence in inflation, while indirectly supporting the multiverse concept. We might be living in the best evidence for infinite other worlds. Yet even this mind-bending possibility assumes our universe has only the 3 familiar dimensions of space. Recent advances in physics suggest reality might be far stranger. What if expansion happens in directions we cannot perceive? The universe might be expanding in directions that don't exist for you. String theory, our most ambitious attempt to unify all physics, requires space to have 9 dimensions instead of the 3 you experience. 6 additional dimensions of space exist right here, right now, curled up so tightly that even particles cannot detect them. These hidden dimensions might be expanding along with the familiar ones. Imagine you're an ant walking on a garden hose. From your perspective, you can move forward or backward along the hose, experiencing what seems like one-dimensional space. But the hose actually has 3 dimensions. The circular dimensions around the hose are so small compared to your size that you cannot perceive them. We might be like that ant, aware of only 3 spatial dimensions, while 6 others remain curled up beyond our perception. If these extra dimensions exist, they could provide the answer to what the universe expands into. Our familiar three-dimensional space might be expanding into the higher dimensional space that contains it, like a balloon surface expanding in three-dimensional air. Our space might be a three-dimensional membrane expanding in nine-dimensional hyperspace. This concept, called the brain-world model, suggests our entire universe is a membrane floating in a higher dimensional space. Everything we can observe, every particle and force except gravity, might be confined to this three-dimensional brain. Gravity alone can escape into the extra dimensions, which explains why gravity is so much weaker than other fundamental forces. The expansion we observe might be our brain stretching within the larger hyperspace. But here's what makes this possibility truly mind-bending. Other brains might exist parallel to ours in the extra dimensions. These parallel universes could be separated from us by less than a millimeter in directions we cannot point to or move in. Another version of you might be reading these words just a tiny distance away in the fourth spatial dimension. These parallel brains could occasionally collide, creating what we would observe as a Big Bang. The cosmic microwave background we detect might be the afterglow of our brain's collision with another brain in hyperspace. This collision would have provided the energy for inflation and set our universe on its current expansion trajectory. Every few trillion years, the brains might collide again, creating a new Big Bang and restarting cosmic evolution. But the mathematics of extra dimensions creates even stranger possibilities. Some models suggest the extra dimensions themselves might be expanding while our familiar three dimensions remain static. From our perspective, we would observe expansion and interpret it as our space growing. In reality, the hidden dimensions might be doing all the expanding. Think of a balloon where the surface stays the same size while the interior volume grows. We live on the surface, so we would never directly detect the interior expansion. Alternative models propose that some dimensions expand while others contract. The universe might be stretching in the directions we can see while shrinking in directions we cannot. The total volume of space could remain constant even though our three-dimensional slice appears to grow. These possibilities remain highly speculative because we cannot directly probe extra dimensions. The Large Hadron Collider, our most powerful particle accelerator, can search for signs of extra dimensions by looking for particles that seem to disappear into hyperspace. So far, no such evidence has been found. Either the extra dimensions don't exist, or they're even more tightly curled than theory predicts. Yet the mathematics of string theory continues to suggest that extra dimensions are necessary for a complete description of reality. If they exist, they fundamentally change what cosmic expansion means. The question, what does the universe expand into, might have a simple answer. It expands into dimensions you cannot see, detect, or imagine. But even if extra dimensions don't exist, the shape of our familiar three-dimensional space might hold surprises. What if space curves back on itself in ways that make the question meaningless? The universe might be shaped like a donut, and expansion might be nothing more than the donut getting fatter. This sounds absurd until you realize that the shape of space determines what expansion means. In a flat, infinite universe, expansion stretches space toward no particular destination. But in a curved, finite universe, expansion might simply increase the size of a closed shape that wraps back on itself. General relativity allows three possible geometries for space. Space could be flat, like an infinite sheet of paper. Parallel lines would remain parallel forever. The angles of a triangle would add up to exactly 180 degrees. This is the geometry most people imagine when they think about space. Space could be curved, like the surface of a sphere. Parallel lines would eventually meet. Triangle angles would add up to more than 180 degrees. In this closed geometry, you could travel in what feels like a straight line and eventually return to your starting point. Or space could be curved like a saddle. Parallel lines would diverge. Triangle angles would add up to less than 180 degrees. This open geometry stretches infinitely, but with negative curvature. Current observations suggest our universe is either flat or so close to flat that any curvature is undetectable. But flat doesn't necessarily mean infinite. A sheet of paper is flat, but you can roll it into a cylinder or connect its edges to make a donut shape. The geometry remains flat locally, but the overall topology becomes finite and closed. Our universe could have this kind of structure. If space wraps around itself, then asking what it expands into becomes meaningless. A donut getting larger doesn't expand into anything. It simply becomes a bigger donut. The surface area increases, but there's no external space being filled. This wrapped geometry would create observable effects. In a donut-shaped universe, light could travel around the entire universe and return to its starting point. We might see multiple images of the same distant galaxies in different directions in the sky. The cosmic microwave background might show repeating patterns where light has circled the universe multiple times. Astronomers have searched for these signatures and found none. Either our universe is much larger than the observable region, or it doesn't wrap around itself at the scales we can detect. The universe might be a donut, but a donut so large that light hasn't had time to circle it even once. But the shape question becomes even more complex when you consider that space and time form a unified four-dimensional fabric. The universe's shape includes not just the three dimensions of space, but also the dimension of time. Expansion doesn't just stretch space. It affects the relationship between space and time throughout the cosmos. In the early universe, when everything was compressed, time itself flowed differently than it does today. Clocks would have ticked at different rates. The very concept of simultaneity across vast distances would have had different meaning. As space expands, it carries time along with it. This space-time expansion creates effects that seem impossible. Distant galaxies are moving away from us faster than light. Yet they're not actually moving through space at all. Space itself carries them along, stretching the time dimension as well as the spatial dimensions. From the galaxy's perspective, it remains stationary while we race away at tremendous speed. This relativity of motion means that expansion looks the same from every location in the universe. Every observer sees themselves at the center of expansion with everything else moving away. There is no preferred reference frame, no absolute center, no edge that could expand into something else. The universe expands by becoming more itself, not by growing into something else. Yet this philosophical resolution of the expansion paradox raises new questions about the nature of time itself and whether the flow of time might be linked to the expansion of space in ways we are only beginning to understand. How does the stretching of space affect the dimension we call time? Time itself is stretching along with space, and this changes everything about how the universe ages. When Einstein revealed that space and time form a unified fabric called spacetime, he showed us that you cannot stretch one without affecting the other. As cosmic expansion pulls space apart, it also stretches the flow of time throughout the universe. This isn't just theoretical physics, it's measurable reality. Imagine you're watching a distant galaxy through a telescope. That galaxy appears to be moving away from you due to expansion. But here's what breaks your intuition. Events in that galaxy appear to unfold in slow motion compared to events happening nearby. A supernova explosion that takes 3 weeks to brighten and fade in a nearby galaxy takes much longer when observed in a distant, rapidly receding galaxy. This time, dilation happens because the light carrying information about those events gets stretched during its journey. Not just the wavelength of the light, but the time intervals between the light pulses get extended. The universe literally stretches time itself. In regions of space that are expanding rapidly relative to us, time appears to crawl. Here's the number that demonstrates this effect. Light from galaxies at the edge of our observable universe is redshifted by a factor of about 10. This means those galaxies were moving away at roughly 90% the speed of light when they emitted that light. Events in those galaxies appear to unfold 10 times slower than events happening here. This creates a bizarre situation where the age of the universe depends on your location. From our perspective, the universe is 13.8 billion years old. But if you could somehow observe from one of those distant, rapidly receding galaxies, our region of space would appear much younger. Time itself has been stretched by expansion. This temporal stretching reveals something profound about the nature of cosmic evolution. The early universe didn't just contain more compressed space. It contained more compressed time. Processes that take billions of years today happened much faster in the dense early cosmos. The formation of the first stars, the first galaxies, the first black holes all occurred in a universe where time flowed differently than it does now. But expansion affects more than just the rate of time's passage. It changes the very concept of simultaneity across cosmic distances. In our everyday experience, simultaneity seems obvious. If two events happen at the same time, they happen at the same time everywhere. But relativity and cosmic expansion shatter this assumption. Events that appear simultaneous to you happen at different times, according to observers in distant galaxies. There is no universal now that applies everywhere in the universe. This breakdown of simultaneity means that asking what the universe is doing right now becomes meaningless on cosmic scales. Different observers define now differently. The present moment is local, not universal. As expansion accelerates, these temporal effects become more dramatic. Dark energy's influence grows stronger over time, stretching space faster and faster. This acceleration also accelerates the stretching of time. Future civilizations in our galaxy will observe even more extreme time dilation effects when looking at distant galaxies. Eventually, expansion will stretch time so much that distant events appear completely frozen. But this accelerating expansion raises a terrifying question about the ultimate fate of everything. What happens when expansion becomes so extreme that it overwhelms every force in nature? The universe is racing toward a state so cold and empty that no process capable of generating energy will remain possible anywhere, ever. This inevitable destination, called heat death, represents the ultimate victory of cosmic expansion over every other force in nature. As space continues stretching, it will spread matter and energy so thin that the universe becomes a lifeless uniform void at nearly absolute zero temperature. The timeline for this cosmic ending is almost incomprehensibly long. In about 100 billion years, the last stars will exhaust their nuclear fuel and fade to darkness. No new stars will form because expansion will have stretched matter too thin for gravity to gather new stellar nurseries. The universe will enter what cosmologists call the degenerate era, dominated by cold stellar remnants. But that's just the beginning of the end. After 10 to the power of 34 years, even protons will decay into lighter particles. The atoms that make up your body, the atoms that form planets and stars, will spontaneously disintegrate. Matter as we know it will cease to exist. Only electrons, positrons, and photons will populate the expanding void. These numbers dwarf human comprehension. If the current age of the universe were compressed to a single second, the proton decay era would last longer than a billion years. Yet even this unimaginable stretch of time represents just a tiny fraction of the universe's future. After 10 to the power of 100 years, black holes will become the only significant sources of energy in the cosmos. Black holes evaporate through Hawking radiation, slowly converting their mass into particles and energy. Stellar mass black holes take longer than the current age of the universe to evaporate completely. Supermassive black holes, the giants lurking at galaxy centers, will persist for 10 to the power of 100 years. When the last black hole finally evaporates, the universe will achieve perfect heat death. No temperature differences will exist anywhere. No chemical reactions will be possible. No computation will occur. No life of any kind can survive. The cosmos will have reached maximum entropy, a state of perfect equilibrium where nothing interesting can ever happen again. This fate seems inevitable given our current understanding of physics. Dark energy accelerates expansion, spreading matter and energy across ever-increasing volumes of space. Unless dark energy somehow changes its behavior, expansion will continue forever, carrying the universe toward this cold, empty destiny. But expansion creates an even more immediate threat to the far future. As space stretches faster, distant galaxies disappear from our observable universe. They don't get destroyed. They simply recede so rapidly that their light can never reach us again. From our perspective, they fade away and vanish. In about 150 billion years, only our local group of galaxies will remain visible. Future astronomers living in the Milky Way will observe a universe that appears to contain only a few dozen galaxies surrounded by empty space. They will see no evidence of cosmic expansion because all the expanding regions will lie beyond their observational horizon. These future scientists might conclude they live in a small, static universe. The cosmic microwave background, our clearest evidence for the Big Bang, will also disappear. Expansion will redshift this ancient radiation to such long wavelengths that it becomes undetectable. Future instruments will detect no trace of this primordial light. Without the microwave background, future cosmologists will lack proof that the universe ever had a beginning. The redshift-distance relationship that revealed expansion to us will become unmeasurable. With no distant galaxies visible, future astronomers cannot discover Hubble's law. They will have no way to detect that space is stretching. Their universe will appear completely static. These future scientists might develop entirely different cosmological theories. They might conclude that their single giant galaxy has existed forever in an infinite, unchanging void. They might never imagine that their cosmos once teemed with billions of galaxies racing apart due to cosmic expansion. They will inhabit a universe stripped of its own history, but the loss of cosmic perspective extends even further. Future observers will also lose access to information about the laws of physics that governed early cosmic evolution. The nuclear processes that forged the first elements will have finished billions of years earlier. Evidence for Big Bang nucleosynthesis will exist only in the chemical composition of old stars. These future civilizations will face a profound epistemological crisis. They will possess the same intelligence and technological capabilities as modern humans. But they will observe a universe that provides few clues about its own nature. Their scientific method will work perfectly, but it will lead them to incorrect conclusions about reality. This raises disturbing questions about our own cosmic knowledge. Are we similarly deceived by observing the universe at a particular epoch? Do we miss crucial evidence that was visible to earlier observers but has already faded beyond detection? Perhaps civilizations that emerged shortly after the Big Bang could observe phenomena that remained forever hidden from us. The parallel extends to the far future of cosmic expansion itself. As space continues growing, even the processes that currently sustain life will eventually become impossible. Star formation will cease when gas becomes too diffused to collapse under gravity. Existing stars will exhaust their fuel and fade to darkness. Black holes will evaporate through Hawking radiation, leaving behind only elementary particles scattered across vast emptiness. The universe will approach perfect heat death. Any observers who somehow survive to that epoch will inhabit a cosmos even more deceptive than the one facing future astronomers. They will see no stars, no galaxies, no structure of any kind. They might conclude that their universe consists only of a few particles drifting through infinite empty space. They will have no way to imagine that their reality once contained trillions of galaxies. This progression from richness to emptiness represents the ultimate consequence of asking what the universe expands into. The question assumes that expansion must have a destination, a goal, a final state that justifies the journey. But expansion might be its own justification, a process that creates meaning through temporary complexity rather than permanent achievement. The structures we observe today, from galaxies to planets to life itself, exist precisely because expansion provides the dynamic backdrop that allows them to emerge. Without expansion, the universe would either collapse immediately or remain forever frozen in simplicity. Expansion creates the very stage upon which cosmic drama unfolds. Yet there exists an even more catastrophic possibility. What if dark energy doesn't remain constant? What if it strengthens over time? In about 22 billion years, dark energy might become so powerful that it tears apart every atom in the universe, shredding reality itself down to its fundamental components. This catastrophic end, called the Big Rip, would make heat death look gentle by comparison. Instead of slowly fading away over trillions of years, the universe would destroy itself in a final spasm of accelerating expansion that overwhelms every force in nature. The destruction would follow a terrifying timeline. About 1 billion years before the Big Rip, dark energy becomes strong enough to overpower gravity on galactic scales. Galaxy clusters dissolve as space expands too rapidly for gravity to hold them together. Individual galaxies drift apart into the growing void, isolated from each other forever. 200 million years before the end, expansion tears apart individual galaxies. Stars get ripped away from their galactic homes and scattered across space. The Milky Way dissolves. Andromeda disintegrates. Every galaxy becomes a collection of isolated stars racing away from each other as space stretches faster than gravity can pull them back together. 30 minutes before the Big Rip, expansion overcomes the gravitational binding of solar systems. Earth gets torn away from the Sun. The Moon spirals away from Earth. Every planet in every solar system throughout the universe suddenly finds itself alone in expanding space, warming only from its own internal heat as its parent star recedes into darkness. The last 30 minutes of existence become increasingly violent. 90 seconds before the end, expansion becomes strong enough to overcome molecular bonds. The atmospheric gases surrounding every planet disperse into space. Oceans boil away not from heat, but because the space between water molecules expands faster than intermolecular forces can maintain liquid cohesion. 10 to the power of -12 seconds before the Big Rip, atomic nuclei disintegrate. The strong nuclear force that binds protons and neutrons together finally succumbs to the relentless stretching of space. Every atomic nucleus in the universe spontaneously breaks apart into individual protons and neutrons. The matter that formed stars, planets, and life reverts to its most fundamental components. At the moment of the Big Rip, even space and time themselves might disintegrate. Some models suggest that space can only stretch so far before the very concept of distance breaks down. The metric that defines how to measure lengths and time intervals becomes infinite. Causality fails. The universe doesn't just end, it becomes physically meaningless. But this nightmare scenario depends on dark energy behaving in a specific way. If dark energy remains constant, the Big Rip will never occur. The universe will expand forever, approaching heat death gradually. Only if dark energy strengthens over time does the Big Rip become inevitable. Current observations suggest dark energy has remained roughly constant throughout cosmic history, but the data isn't precise enough to rule out slow changes. Future measurements of distant supernovae and other cosmic distance indicators will determine whether dark energy is strengthening. If it is strengthening, we can calculate exactly when the Big Rip will occur. The calculation depends on how rapidly dark energy increases. Conservative estimates place the Big Rip about 22 billion years in the future. More aggressive models suggest it could happen much sooner, possibly within a few billion years. Either timeline provides little comfort for long-term cosmic planning. Yet even this ultimate destruction might not represent the end of everything. Some theories suggest that the Big Rip could trigger new episodes of cosmic inflation, creating fresh universes from the wreckage of the old one. The tearing apart of space-time might seed new realities. But before we can understand these cosmic endings, we must examine how scientists measure the expansion that drives them. The story of cosmic expansion began with observations, not theories. How do you measure something as vast as the stretching of space itself? Astronomers measure the expansion of the universe by turning exploding stars into cosmic yardsticks, using the brightness of stellar death to map the growth of space itself. The challenge seems impossible. How do you measure distances to objects billions of light years away? How do you determine whether those objects are moving away from you? How do you distinguish between motion through space and the expansion of space itself? The answer lies in exploiting the predictable behavior of dying stars. Type Ia supernovae occur when white dwarf stars accumulate too much matter from companion stars and explode with nearly identical brightness. These stellar explosions release the same amount of energy regardless of where they occur in the universe, making them perfect standard candles for distance measurement. Here's how the measurement works. When a Type Ia supernova explodes in a nearby galaxy, astronomers measure its apparent brightness and compare it to the known intrinsic brightness of such explosions. The difference tells them exactly how far away the explosion occurred. Basic physics objects appear dimmer when they're farther away. Simultaneously, they measure the redshift of the host galaxy by analyzing the wavelengths of light from the explosion. Redshift indicates how much the wavelength of light has been stretched during its journey through expanding space. Higher redshift means the light traveled through more expansion, indicating both greater distance and earlier cosmic time. By plotting distance versus redshift for hundreds of supernovae, astronomers map the expansion history of the universe. If expansion were constant, the relationship would form a straight line. If expansion were slowing due to gravity, distant supernovae would appear closer than expected. If expansion were accelerating, distant supernovae would appear farther away than expected. The data clearly shows acceleration. Supernovae that exploded when the universe was younger appear fainter than they should if expansion were constant. This means they're farther away than expected, indicating that space expanded more than anticipated during the light's journey to Earth. Dark energy has been accelerating expansion for billions of years. But measuring cosmic expansion requires more than just supernovae. Astronomers use multiple techniques to build what they call the cosmic distance ladder, with each rung calibrated using the previous one. The bottom rung uses parallax measurements to nearby stars. As Earth orbits the Sun, nearby stars appear to shift position against the background of more distant stars. This parallax angle, combined with Earth's orbital diameter, provides precise distances to stars within a few hundred light years. These parallax distances calibrate the next rung Cepheid variable stars. Cepheids pulsate with periods directly related to their intrinsic brightness. By measuring a Cepheid's pulsation period, astronomers know exactly how bright it should appear. Comparing this to its observed brightness gives its distance. Cepheids can be seen in galaxies up to 100 million light-years away. Cepheid distances calibrate the supernova measurements, which extend the distance ladder to billions of light-years. Each rung depends on the accuracy of the previous rungs, making the entire cosmic distance scale vulnerable to systematic errors. This vulnerability has created one of the biggest controversies in modern cosmology. Different measurement techniques give slightly different values for the Hubble constant, the number that describes how fast the universe expands. Local measurements using the distance ladder suggest space expands at about 73 kilometers per second per megaparsec, but measurements from the cosmic microwave background suggest a lower value of about 67 kilometers per second per megaparsec. This 6% discrepancy might not sound significant, but it represents a crisis in cosmology. Either one of the measurement techniques contains unknown errors, or our understanding of cosmic evolution is fundamentally flawed. The resolution might require new physics, or the discovery of systematic errors that have evaded detection for decades. Yet, despite this controversy, both techniques agree on the most important conclusion: the universe is expanding, and that expansion is accelerating. But how do scientists translate these observational measurements into mathematical descriptions of cosmic evolution? The entire expansion history of the universe can be captured in a single mathematical function that describes how space grows over time. And this function reveals the cosmic future. Scientists call this the scale factor, usually represented by the letter A. This simple variable encodes everything about how distances change as the universe evolves. When the scale factor doubles, all distances double. When it triples, all distances triple. The scale factor makes cosmic expansion mathematically precise. By convention, cosmologists set the scale factor to 1 at the present time. This means that earlier in cosmic history, when the universe was smaller, the scale factor was less than 1. In the future, when the universe will be larger, the scale factor will exceed 1. Here's what makes this framework so powerful. The scale factor connects observable quantities to cosmic time. When you observe a galaxy with redshift z, you're seeing it at a time when the scale factor equaled 1 divided by 1 plus z. A galaxy with redshift 1 existed when the scale factor was 0.5, meaning the universe was half its current size. This allows astronomers to reconstruct cosmic history from redshift measurements. Light from the cosmic microwave background has redshift of about 1090. This radiation comes from when the scale factor was roughly 0.001, meaning the universe was 1,000th its current size in each dimension. The volume of space was 1 billion times smaller when that light was emitted. But the scale factor does more than describe the past. Combined with Einstein's field equations, it predicts the future evolution of cosmic expansion based on the current contents of the universe. The acceleration of expansion depends on how the scale factor changes with time. If the scale factor grows linearly, expansion proceeds at constant rate. If the scale factor grows faster than linearly, expansion accelerates. If it grows slower than linearly, expansion decelerates. Current observations show that the scale factor has been growing faster than linearly for about 5 billion years, confirming cosmic acceleration. The mathematics reveals 3 possible futures, depending on the properties of dark energy. If dark energy remains constant, the scale factor will grow exponentially forever. Space will expand at an accelerating rate, but the acceleration itself will approach a constant value. This leads to heat death as matter spreads ever thinner across growing space. If dark energy strengthens over time, the scale factor will grow faster than exponentially, leading to the Big Rip scenario where expansion eventually overcomes all forces. If dark energy weakens or becomes negative, the scale factor might eventually stop growing and begin shrinking, leading to a big crunch where the universe collapses back on itself. Current data suggests the first scenario is most likely, but the scale factor framework reveals something even more profound about the nature of cosmic expansion. The expansion rate at any given time depends only on the total energy density of the universe at that time. More energy density means faster expansion. In the early universe, when matter and radiation were compressed into a small volume, the energy density was enormous. This drove very rapid expansion that gradually slowed as the universe grew and energy density decreased. About 5 billion years ago, dark energy became dominant and expansion began accelerating again. The scale factor mathematically encodes this entire transition from deceleration to acceleration. By fitting theoretical curves to observational data, cosmologists can determine the relative amounts of matter, radiation, and dark energy at different epochs. These calculations reveal that our universe is currently about 68% dark energy, 27% dark matter, and 5% ordinary matter. The scale factor approach also predicts how these percentages will change over time. As space expands, matter becomes more dilute, but dark energy maintains constant density. This means dark energy's influence will grow stronger in the future. Eventually, dark energy will dominate so completely that expansion approaches pure exponential growth. But this mathematical framework for understanding expansion rests on insights that emerged from one of the greatest scientific blunders in history. What happens when a genius makes a mistake that accidentally predicts the future? Albert Einstein added a term to his equations of general relativity that he later called his greatest blunder. But that term turned out to be essential for understanding the accelerating expansion we observe today. In 1917, Einstein faced a problem with his newly completed theory of general relativity. The equations predicted that the universe should either be expanding or contracting. They allowed no static, unchanging cosmos. But everyone knew the universe was static and eternal. At least that's what astronomers believed at the time. The idea of a dynamic, evolving universe seemed absurd. How could the entire cosmos be changing? Where would it expand to? What would drive such expansion? Einstein trusted the observational evidence and modified his equations. He added what he called the cosmological constant, represented by the Greek letter lambda. This term acted like a repulsive force that could exactly balance gravity's attractive pull, allowing the universe to remain static despite containing matter. The cosmological constant represented the energy of empty space itself. Einstein envisioned this space energy as a fundamental property of the vacuum, creating a gentle outward push that prevented gravitational collapse. Just enough repulsion to balance attraction. Just enough to keep the universe perfectly balanced and unchanging. For more than a decade, this seemed like a reasonable solution. Then, Edwin Hubble discovered that distant galaxies are racing away from us. The universe wasn't static after all. It was expanding just as Einstein's original equations had predicted. The observational evidence that convinced Einstein to add the cosmological constant was simply wrong. Einstein quickly abandoned the cosmological constant, calling it his greatest blunder. If he had trusted his original equations instead of the flawed observations, he would have predicted cosmic expansion decades before Hubble discovered it. Einstein could have been remembered as the scientist who predicted the expanding universe purely from theoretical reasoning. Instead, he introduced a term he thought was unnecessary and then spent years trying to remove it from physics. But the story doesn't end there. In 1998, astronomers discovered that cosmic expansion is accelerating. Something is pushing space apart with increasing strength. Exactly what Einstein's cosmological constant was designed to do. Einstein's blunder turned out to be essential for understanding the universe. The accelerating expansion requires some form of dark energy that behaves exactly like Einstein's cosmological constant, a uniform energy density that fills all of space and creates repulsive gravitational effects. Current observations suggest the cosmological constant provides the best fit to the data. If this interpretation is correct, then Einstein's intuition about the energy of empty space was remarkably prescient. He realized that vacuum itself might possess energy and gravitational effects. Even though he added this insight to his equations for the wrong reasons, the physics was sound. The value of the cosmological constant in our universe is tiny but non-zero. Each cubic centimeter of empty space contains about 10 to the power of -10 joules of dark energy. This seems insignificant, but when multiplied by the vast volume of the observable universe, it totals more energy than all the matter and radiation combined. Einstein's supposedly unnecessary term dominates cosmic evolution. But the cosmological constant creates a new problem that Einstein never anticipated. If vacuum energy drives acceleration, why is the value so small? Quantum field theory predictions suggest vacuum energy should be 10 to the power of 120 times larger than observed. This vacuum catastrophe represents one of the deepest mysteries in physics. Either our understanding of quantum mechanics is fundamentally flawed, or some unknown mechanism suppresses most of the vacuum energy while allowing just enough to remain active to drive observed acceleration. Resolving this mystery might require entirely new physics beyond anything Einstein imagined. Alternative theories propose that dark energy isn't a cosmological constant at all, but rather a dynamic field that changes over time. These models might avoid the vacuum catastrophe while still explaining accelerated expansion. But current observations favor Einstein's original insight about the energy of empty space. The irony is profound. Einstein added the cosmological constant to prevent expansion, then removed it when expansion was discovered. Modern cosmology has restored it to explain why expansion is accelerating. His greatest blunder became his most prescient insight. Yet even Einstein's genius built upon observations that revolutionized our understanding of the cosmos. What happens when an astronomer points a telescope at the sky and discovers that everything we thought we knew about the universe is wrong? Edwin Hubble spent night after night in 1929 measuring the distances and velocities of distant galaxies and accidentally discovered that the entire universe is flying apart. Working at Mount Wilson Observatory with the largest telescope in the world, Hubble was trying to settle a debate about the nature of spiral nebulae. Were these cloudy objects part of our Milky Way galaxy? Or were they separate galaxies at vast distances? His measurements proved they were separate galaxies, but that wasn't the revolutionary discovery. Using Cepheid variable stars as distance indicators, Hubble calculated that these spiral galaxies lay millions of light-years away, far beyond the boundaries of the Milky Way. This expanded the known universe from a single galaxy to a cosmos filled with countless galaxies. But as he plotted galaxy distances against their velocities, Hubble noticed an impossible pattern. Every galaxy was moving away from us, not just a few galaxies, not just distant galaxies. Every single galaxy he could measure showed red-shifted light, indicating motion away from the Milky Way. This seemed to place Earth at the center of a cosmic explosion. More disturbing still, the farther away a galaxy was, the faster it appeared to be receding. Galaxies twice as distant moved away twice as quickly. Galaxies 3 times farther moved 3 times faster. This relationship, now called Hubble's law, suggested a direct proportionality between distance and recession velocity. At first, Hubble interpreted this pattern as evidence for motion through space. He imagined galaxies racing away from us through a static cosmic arena, like debris from an explosion expanding into empty space. But this interpretation created impossible problems. If all galaxies were moving away from us, it would mean we occupy the special center of the universe. This violated the Copernican principle that Earth holds no privileged position in the cosmos. Why should we be at the center of everything? The resolution came from understanding that space itself was expanding. Imagine dots painted on a deflating balloon, but run the process in reverse. As the balloon inflates, every dot sees every other dot moving away. The farther apart 2 dots are, the faster they separate. Yet no dot is special. No dot sits at the center of expansion. Each dot experiences the same pattern Hubble observed. This insight transformed Hubble's discovery from a measurement of galactic motion to evidence for cosmic expansion. Galaxies aren't moving through space. Space itself is stretching, carrying galaxies along like raisins in rising bread dough. Hubble's law became the first observational evidence for the expanding universe. The proportionality constant in Hubble's law, now called the Hubble constant, describes how fast space expands. A larger Hubble constant means faster expansion. A smaller constant means slower expansion. Hubble's original measurements gave a constant about 7 times larger than modern values, suggesting a universe only 2 billion years old. This created problems because geological evidence indicated Earth was older than 2 billion years. How could Earth be older than the universe itself? The error lay in Hubble's distance measurements. He confused 2 different types of variable stars, leading to systematic underestimation of galactic distances. When astronomers corrected these errors, the age of the universe increased to comfortable values well above Earth's age. But Hubble's discovery of the distance-velocity relationship remained valid. Modern measurements confirm that expansion follows Hubble's law to remarkable precision across cosmic distances. From nearby galaxies a few million light-years away to the most distant observable galaxies, billions of light-years distant, the relationship holds. This consistency proves that expansion is a global property of space itself. Hubble's work also established the first cosmic distance scale, allowing astronomers to map the three-dimensional structure of the universe. Before Hubble, astronomy was essentially two-dimensional, limited to measuring positions on the sky. After Hubble, cosmology became possible. His discovery transformed our understanding of humanity's place in the cosmos. We don't live in a static, eternal universe. We inhabit a dynamic, evolving cosmos that began in a hot, dense state and has been expanding and cooling ever since. The expanding universe, revealed by Hubble's observations, became the foundation for Big Bang cosmology. Yet all these discoveries, from Einstein's equations to Hubble's observations to modern measurements of dark energy, lead us back to the fundamental question that started our journey. In a universe that creates its own space, that manufactures its own time, and that serves as its own stage, what exactly does it mean to ask what it expands into? The question, what is the universe expanding into, is like asking what's north of the North Pole, and understanding why reveals the deepest truth about the nature of reality itself. When you ask what the universe expands into, you're making an assumption that seems perfectly reasonable, but is actually impossible. You're assuming that expansion requires a pre-existing space to expand into, like a balloon needing air or a city needing countryside. But the universe is not like a balloon. The universe is space itself. When space expands, it doesn't grow into something else. It creates the very concept of something else as it grows. There is no external arena because the universe defines what external means. This isn't a limitation of human language or a failure of scientific imagination. It's a fundamental feature of reality. Before expansion, the concepts of into and outside don't exist. Expansion doesn't just create more space. It creates the logical framework that makes spatial relationships meaningful. The universe doesn't expand into anything because it creates the very notion of anything as it expands. Think of it this way. Asking what the universe expands into is like asking what caused the first cause, or what contains the container of everything. The question assumes categories that only make sense after the thing you're asking about has already happened. The universe expands by becoming more universe, not by growing into non-universe. This realization transforms our understanding of cosmic expansion from a mechanical process to something far more profound. Expansion isn't just the universe getting bigger, it's reality bootstrapping itself into existence. Every cubic inch of new space that comes into being creates new possibilities for matter, energy, structure, and complexity. The universe doesn't expand towards some predetermined goal, it expands into the infinite potential for what can be. We are not passengers on a cosmic vehicle traveling towards some destination. We are part of the process by which reality creates itself. Our consciousness, our questions, our desperate need to understand what the universe expands into, these are all expressions of the universe coming to know itself. The expansion we observe isn't separate from us. We are expansion. We are space and time and matter and energy organizing themselves into patterns complex enough to ask questions about their own existence. This perspective resolves the paradox of cosmic expansion while revealing an even deeper mystery. If the universe creates its own space and time, if it serves as its own stage and audience, then what we call existence might be far stranger than any science fiction has imagined. We might be living inside a self-creating, self-sustaining process that has no beginning or end, no inside or outside, no purpose beyond the magnificent fact of its own becoming. The universe expands into itself, creating infinite room for infinite possibilities, including the possibility of beings like us, who can stand in awe of the whole impossible, beautiful process. The question, what does the universe expand into, led us on a journey through inflation and dark energy, multiverses, and quantum foam, the beginning and end of time itself. But the deepest answer was always hiding in plain sight. The universe expands into mystery, into wonder, into the endless capacity for more questions, more discoveries, more moments of recognition that we are part of something vastly larger than ourselves, yet intimately connected to our smallest thoughts. We are the universe asking what it expands into. We are the expansion asking where it's going. We are space and time, awakening to their own existence and marveling at the infinite creativity of the process that brought us into being. And in that recognition, the question transforms from a puzzle to be solved into a celebration of the magnificent impossibility of existence itself. The universe doesn't expand into anything because it is everything. It is the question and the answer, the journey and the destination, the mystery and the revelation, all rolled into one inexplicable, awe-inspiring, ever-growing whole.